very complex slide. So in this first presentation, I will have only this one slide. It presents the architecture, overall architecture of the C4IoT framework. Here we can distinguish three layers of the architecture. They are horizontal edge node layer down here below, and then in the middle of the figure you can see field gateway layer, and on top of it the largest one is the cloud layer. There are also, these are layers of architecture. There are also levels of security that you can see here in the left side, but we will not discuss them today. All details, all the possible details of the architecture are described in deliverable 1.3, and you can download the deliverable freely from it's public from the project website. There you can find every possible detail about the architecture. But let's now focus on overall picture and how things work. So if we start with the edge nodes, you can see that we have at the edge node layer we have trucks and warehouses that belong to a logistics use case, one of the two use cases that we have described in the project. And the other is smart factory use case. In any case, we have some devices attached to the factory items, logging what's going on. So in smart factory use case, we have single board computers like Raspberry Pis attached to maybe robot hands and other types of devices that record data. And in the logistics use case, we have trucks that carry around containers with supplies and parts, and every container has a microcontroller attached to it. So microcontroller, that's a device with low processing power and smaller capacity of memory, but it records what goes on there. And even here with these devices that do not have a lot of processing power, and microcontrollers are even battery operated, we have some lightweight, as you can see, lightweight anomaly detection. So later we will describe what's going on. So there are some lightweight autoencoders, so neural networks running on those devices and doing some lightweight anomaly detection. So they detect some anomaly. If they detect it, they attach the confidence score to it and send it upwards through various channels. We will not, you will hear details about that a bit later also. So in the field gateway layer, in both use cases, we have field gateway server or multiple servers that are much more powerful. And here is where we can run intermediate complexity anomaly detection. So they know what goes on with all the attached devices that are doing lightweight anomaly detection. They're getting the data from them, and based on the confidence score, decide if anomaly is already detected or if additional processing is needed here with much more powerful machines in the field gateway layer. So you see here, you also describe details. There's a offloading decision mechanism, a tool that decides in which cases data information needs to be offloaded for further processing. And so this is the intermediate complexity anomaly detection you can see here. And here up in the cloud, there's advanced anomaly detection component in the cloud running in a distributed environment. The most powerful anomaly detection goes on there. So that's That's where the data goes, the flow of the data from the edge node layer to field gateway layer to the cloud layer. Concerned with detection of anomalies, of anomalous behavior, and so on. And now, when an anomaly is detected, we have some components that belong to the mitigation engine. That when some anomalous behavior happens, they try to mitigate the consequences. And so the data goes through the security assurance module. You can see that on the right side. That then communicates with the mitigation engine, and within the mitigation engine, three components. BINSEC continuous verification. It checks for anomalies in the firmware. Checks the firmware of those devices at the edge for anomalies. And there's VariMOS. So high-level reconfiguration search, that's the heart of the mitigation engine, that based on all the data it's collected through the SDN controller, then tries to mitigate the anomaly, maybe shut down some parts of the network, maybe reroute traffic through other parts of the network, and so on. So it then goes down and mitigate whatever it can mitigate, whatever happened, whatever was detected. There are also, well, I don't see them because my video is there. I will move it to the left side. You can see that there are components related to advanced visualizations of what goes on here, and we will see the demonstration through those components. That's advanced visualization. We will see an example of what goes on in one of the scenarios that's been finished by now. Okay, I covered only basic parts, some basic elements of the architecture. I intentionally did not mention the other components that you can see here because we don't have that much time now, but again, you can find all the details in a public deliverable 1.3 system architecture. Okay, based on this description, now we will of the architecture. Now we will hear the description of the use cases I mentioned. There are two use cases, and now we will hear a more detailed description by Julian.
Okay.
So I will stop sharing. Yeah.
Yep. So I will share my screen and video also. So good afternoon to everybody from my side. So I'm Julien Mascolo. I'm working in FIAT Research Center. Okay, let me have the presentation in full screen mode. Okay, so I will briefly give you an overview of the business cases, of the value of also that we see in these applications, and briefly describe the two use cases that we have defined for this project. So this is in a nutshell what we will see in this presentation. Very short one, but if other questions are raised, or you can also contact me directly or have some questions at the end of this presentation. So who we are FIAT Research Center. So actually we in a few months we will even bigger than that, actually what we are, because we are in the process of merging with another competitor in the sector, Peugeot Citroën. And so we are the group in FCA, Fiat Chrysler Automobiles. We are the group involved in the definition of innovation, taking into account its potential for exploitation in all the plants that we have worldwide. So that's why we have selected this project for its, and we are driving the requirements for these projects because it's completely pertinent to our research agenda in FIAT, and in particular, we assess that there is a big potential for application in our companies and plants. So what is the initial motivation for us in participating in this project? We have a lot of devices, whether CPS, IoT, other sensors and devices scattered all over the value chain, from our supplier to our plants. So these devices are involved in, for example, inbound logistics processes. Just think of containers, thousands of containers going through the logistic process from the supplier to our plants. And then we have all the internal operations of the plants. Think, for example, of sensors, wireless sensors attached to robots, whether moving or fixed robots. Think of the same devices that I mentioned before, the devices attached to the containers. So we have a huge quantity of devices. Many of them are wireless. A huge quantity of actors also involved in these business processes. Many of them are not internal to the company. Think of the external logistic providers, the providers of the hardware itself. For example, sensor embedded in our robots. So we have this variety of devices, this variety of actors involved, and we have a lot of risks related to that. The risk of tampering with the devices, to use them as a door to access our internal systems, and this has a terrific impact on the processes themselves. So meaning losing production, decreasing the saturation of the systems, limiting the labor of the staff, and related to the persons also there could be an impact on the safety. Think of the robots interacting with people. We have now an increasing number of robots enabling human-robot collaboration. So think of these robots being used by or being tampered with by external malicious actors. So this is a little bit what we started with this view of the threats that we have in the processes. So we went on then to define two different business scenarios. One is on the inbound logistics. So that's the process of sourcing components and subsystems to our plants. That's the first one. And the second one is on the internal process of the plant, whether it's assembly or welding with robots, or moving robots in the, for example, for logistics inside the plant. This is the the objective of the second scenario. So, what do we expect from C4IoT? We expect this visual security platform, what we call it. Maybe it's not how maybe the more academic partners or the technical partners call it, but this is how we sell it and how we see it in our company. A security platform, and we'll see a generic view of how it feels. A security platform enabling the monitoring of these systems, the analysis of the threats, the representation of these threats and their impact on the systems, and the definition for sure, the definition of recovery alternatives. So in a nutshell, that's what we are here for and what we expect from this platform. So on the right-hand part, this is our view of it. So in this life cycle, let's say, of the productive system, we have an incoming threat identified by the platform. Its impact on the system is assessed. Some recovery actions, part of them can be automated, part of them can remain, can still involve some human operators. So these recovery actions are defined, and then they are enacted, and then there is this continuous monitoring which continues to monitor our system. So on the left-hand part, you have a list of the functionalities that we expect. So that means real-time threats analysis, evaluation of the impact, definition of the potential actions, and as we are very keen on that, definition of some visualization, able to understand what is going on and what is the impact and what has been performed to tackle the issues. So as I said before, the benefits are enormous, ranging from the saturation of the systems to the actual throughput of the system. What we call job per hour here is the number of vehicles that we assemble per hour. So this is also in terms of OEE, so ensuring that our systems are working at full speed and with the minimum cost. And then I also discussed about potential safety issues for the operator, and that's for sure the first in the list from our point of view. The enablers developed in the project, we developed some hardware dedicated to the logging of the and some sensors to monitor the inbound logistics, and then of course all the other strategies and systems that we discussed before in the architecture and that we will discuss afterwards in the more technical insight. This is the enabler. These are the enablers that we see for this application. So from my side, that's all. I will be happy to answer some questions, or please contact me via mail if you need some more information that I can provide without jeopardizing our our participation to this project and our internal our IP, let's say. Mm-hmm. Okay, thank you. If there are questions, I will be happy to answer them now. Okay, so Marie-Noël, I'll give you the token again.
Yeah. Is there? Yeah, good afternoon for everybody. Yeah, good afternoon, everybody. Let me share my screen. Okay, so good afternoon for everybody. This is Nikos Evangeliou from ITML. In this section, I will present you the C4IIoT sorry, minimum viable product. It's the initial integrated version of the C4IIoT system, which demonstrates the functionality of the system based on predefined basic scenarios. Logistics and smart factory are the two use cases selected for the project and are both implemented in the C4IIoT MVP. Even though our intention was to integrate the MVP version in pilot site, the COVID-19 disease outbreak imposed the restrictions or total shutdown and affected the transportation and the travel domain as well for several weeks. To cope with the situation without affecting the development process, we decided to simulate the real environment with synthetic data. The components of the MVP architecture, as you can see here, BACS, MEDICI, traffic analysis, data fusion bus, and AVT will be further presented and analyzed in the following slide. So, this is a high-level overview and the component within each one of the three layers of our system: the edge layer, the field gateway layer, and the cloud layer. So data from the IoT infrastructure are collected and fed to the first tier of lightweight anomaly detection at the lowermost, the edge node layer. This layer contains, as you can see here, two types of devices. In the smart factory, there are single board computers that are directly connected to the devices, such as a tablet, automated ground vehicles, computers, etc. in the factory. And the logistics use case, which includes microcontrollers attached to containers that can be loaded to trucks or stored in warehouses, using mobile networks to communicate with the field gateway. They are present at BACS are present at all. As far as components are concerned, BACS is a collection of software modules based on machine and deep learning algorithms, realizing anomaly detection in IoT sensory data and network flows. They are present at all three layers. So BACS Edge performs anomaly detection, considering data collected at a particular edge node device. BACS field gateway, which is responsible for anomaly detection in data streams coming to a C4IoT field gateway, covering a set of edge node devices. And finally, the BACS cloud, which performs anomaly detection at the level of the whole operational settings. Following this, data is forwarded to the intermediate field gateways layer, the second layer of our architecture. Communication between edge devices and the field gateway is very well encrypted with a standard set of protocols, certificates, procedures, and best practices. So in both use cases, logistics and smart factory, security mechanism will be applied to establish a secure connection with the cloud infrastructure and prevent the disclosure of private information. So Kafka, as you can see here, is used for building real-time streaming data pipelines that reliably get data between systems or applications, as well as a message broker. It offers higher fault tolerance, supporting higher throughput and handling great amounts of data. In this layer, security-aware dynamic offloading decision mechanism decides if an anomaly detection should be triggered in the field gateway or the cloud. Specifically, MEDICI is responsible for deciding which of the low confidence decision of the HBACS anomaly detection module should be further offloaded to another BACS module, either at the field gateway or at the cloud. So if BACS module at the edge has low confidence on its anomaly detection, the data are sent to MEDICI. And after that, MEDICI decides which BACS module should further analyze the data. It means either field gateway or at the cloud. Moreover, in the smart factory, the field gateway use case will also include the traffic analysis module, which runs on the factory field gateway simulator, inspecting all the traffic which goes through and identifying anomalies to the C4IIoT platform. Finally, data streams are fed to the topmost cloud layer, where we will perform anomaly detection for the complete IoT ecosystem using data aggregated and offloaded from the field gateways. The data streams and the detected anomalies will be saved in the storage and then used by the AVT, the visualization toolkit, that exposes the monitoring and the event detection related information to end user, as you can see here. So this is from my side and the MVP architecture. Thank you very much for attending me. Spiros, the floor is yours. I will stop sharing my screen.
Thank you, Nico. Hi, everybody. I think now you can see my screen. As my colleague Nico said, just to stress it again, the MVP version is of the C4IoT is a working prototype, which acts as a proof of concept for the collaboration between proposed C4IoT models, and showcases the potential of the proposed solution. In the MVP version, we are covering both use cases, the smart factory and the logistics. And now we're going to see the screen of the end user. The end user is the security expert in its case, in the smart factory and the logistics. And from this dashboard, the end user can monitor the selected devices and monitor the events detected in the system. So this is the first screen of the dashboard, the smart factory and the logistics. We can select one of these cases. As I said, the user can follow and monitor the events and the functionality of each device. By selecting the devices, we can see the function of the devices in real time, but by monitoring several features. In this case, we selected to present some GPS coordinates or the acceleration. As you can see, there is a real-time data flow from the selected device. We can see the measurements and a flow with a graphical representation of the measurements. Moreover, we can see information about the status of the device if there is any anomaly detected. At this point, we do not have yet some anomalies. So we can see the normal work of the selected device. Going back to follow the events, the information from the events detected, we can see all in real time, even if there is some anomalies detected or there is the normal functionality of the system. Moreover, we can see information about at which stage the final decision about anomaly or normal status detected is the edge device or the field gateway. as Nikos explained, this coming from the previous stages of anomaly detection. If we want to go more to see more details about the anomalies detected, we can see more detailed information about the device which caused the anomaly, the timestamp, and some measurements at the point of the detect anomaly. Moreover, we have some statistical overviews of the system, like, as I said, where the anomaly detected, the risk type at this stage is always high, but at later stages we can have multiple risk levels, and the events detected from the system. This is the dashboard for the MVP, which enables the overview of the end user, to enable the end user to have an overview of the C4IoT system. The same is at the smart factory use case, with the addition that now we have another level of control, which is the traffic analysis on the field gateway of the smart factory. With the same logic, we can follow this type of anomaly detection also. That from my side. If you have any questions, feel free to ask.
Thank you, Spiros.
Okay, Marie-Noël, the token is yours.
Maybe we can have the question at the end of the InfoDay.
Yeah, sure.
Because the time is going, maybe we can go to the next presentation. Sorry, but we are late.
Great, I'm giving you the token.
Thank you. So, Adam, can you speak on the, or Georgia, I don't know the order, to speak about the adaptive anomaly detection?
Yes, I will start with, I'll share my slide. I will start and
Yes.
Georgia.
Thank you.
Okay, it's me again, Serjan from Novi Sad. Now we will go a bit deeper and present a bit more details about what we call here adaptive anomaly detection. We will describe those, well, BACS, behavioral analysis and cognitive security component that stretches through all three layers of the architecture, and that's the central point of anomaly detection. And then after that, you will hear some information about offloading mechanism from University of Greenwich. Okay, so BACS, behavioral analysis and cognitive security. I'll just move this. Okay, I think this is better. It's a software component responsible for anomaly detection by using machine learning and deep learning, so classical machine learning models and some deep learning models on sensory data and on network traffic flows to detect anomalies in the C4IoT framework. It includes unsupervised anomaly detection. That's what we have implemented for now. So it's not finished. The project is well, roughly 50% finished. So we have unsupervised anomaly detection, and we plan to also have some supervised anomaly detection models, hopefully in the near future for specific security threats. And as I said, And as I presented earlier, anomaly detection within the C4IoT framework goes on all three layers of the architecture: edge node, field gateway, cloud. Let's skip to this figure, to this picture, to see the overall picture first, and then we'll go module by module and see what's inside. So you see at the edge node layer, again, we distinguish between these two lilac boxes between the two use cases. So the left one is a logistics use case, and the right one is the smart factory use case. And in smart factory use case, we have single board computer that's Raspberry Pi or similar that has maybe one gigabyte of memory and relatively powerful processor. Relatively powerful comparing to what we have in logistics use case. It's just a microcontroller in the IoT device. You hear detailed explanation of how does that one look like, but it has low processing power and very small amount of memory available. So for this specific use case, we have this module BACS-C. You see BACS-C, that C means programming language C, it's written in C, and it's lightweight anomaly detection. So what's inside is there are some routines written in pure C without using any libraries, and there's an implementation of the autoencoder. Autoencoders is one model of neural network known to show good results with outlier detection scenarios, but this one is lightweight. It only has one hidden layer, so we could not call that one a deep neural network. It's just a neural network. So implemented from scratch and integrated into the firmware of the microcontroller. So it's integrated into the firmware, and so this device does not have the operating system that you can use to run programs in it. You have to integrate it into the firmware. So that's done within this module, BACS-C. And if we go back to this picture, you see this. It says stable code. So BACS-C is finished. It's stable version, and also this BACS-Pi component. So this Pi means Python. So that's also stable. And as you can see, it stretches through all three layers. It can be used in all three layers of the architecture, but you cannot. You have to run it on something that has an operating system at least. So Raspberry Pi can run Python code, and on the upper layers, some field gateway server of course can run it, and in distributed cloud environment, you can run Python code also. So what's inside and what tools have been used to build it? So you see. I can go to the dedicated slide. Anomaly detection based on outlier detection, classification, and representation learning algorithms. At least these three Python libraries have been used: TensorFlow 2 for deeper autoencoders. So we have in BACS-C, we have lightweight, shallow, called shallow autoencoders. Here we have more processing power, so we can use deeper autoencoders, scikit-learn, and PyOD libraries. And so it has a bunch of methods normally used for anomaly detection, machine learning methods for anomaly detection, like elliptic envelope, local outlier factor, one class support vector machine, isolation forests, K nearest neighbors, and so on. At least 8 or 9 of those methods are implemented here. And yes, it supports both standalone and federated anomaly detection models. So there's also federated learning model implemented that, so federated learning scheme uses a lot of devices at the edge. They update the weights of the branches in the neural network and feed what they learn to the central server that then propagates the new weights to all the others, all the other edge node devices. And finally, as you can see in the cloud layer, we have BACS cloud. So this one is also implemented in Python, but it's different. It runs only in cloud, includes unsupervised, will include supervised anomaly detection. And this one is, as you can see, this one is under construction. So it's in some initial versions of the code. Yeah, here's BACS cloud layer. Okay, supervised and supervised runs in distributed environments. So here in the cloud, we have the most powerful anomaly detection, since we have even more processing power, even more memory available. And what we plan to run here are deep neural networks. So the first idea is, okay, we can use very deep autoencoders. We can stack many hidden layers and use autoencoders like that. But I think in what we discussed last, we plan to also use recurrent neural networks, variational autoencoders, and even Facebook Prophet, a library used for time series and so on. So advanced anomaly detection models that require a lot of processing power, and that's what's going on in the cloud, and we will have some of it implemented by month 18, but it's planned for the second half of the project, to be implemented in the second half of the project. Okay, I hope that I did not use too much time. Then I will leave the floor to Georgia.
Okay. Thank you, Srajan. Not sure whether you can see me.
We can see you, we can hear you.
Okay, great. So the different BACS models that Srajan just described, they basically follow the same logic as most state-of-the-art multi-layer anomaly detection mechanism. That is, they operate into different layers. So we said the first layer is the edge layer at the local IoT device. Then we have the more complex models at the field gateway, and then the even more complex deep learning models in the cloud. And usually what happens is if one of them at the lowest layer suspects an attack, or the confidence level of whether this is a proper normal traffic normal data or not is low, then what the model will do is it will go to another more complex model in the next layer, and then if that confidence level is also low, or there is a suspected attack but not at a very confident level, then that will go to the next layer, which in our case is the cloud layer. In practice, this can be seen as an offloading system, where the offloading decision is taken based only on the confidence level. And if that confidence level is low, then we go to the next layer. So in the next slide, what we are actually envisioning in C4IoT is to make this process more automated, more adaptive. So this is where we use our MEDICI tool, which MEDICI stands for multi-criteria decision support mechanism for IoT offloading. And the idea is now to have the decision of which model should run next if the confidence of the previous model is low, to be done in an automated and adaptive way. So our MEDICI tool will take into consideration not only the confidence level of the detection, but also other context-aware criteria, such as how long will it take in order for it to come up with a decision of whether this is an anomaly or a normal operation, and which means the processing availability, or the network conditions. So if I wanted to run this in the cloud, will my network conditions allow it to be fast enough to have a detection, or is it better to do it at the field gateway layer? And I need to say here that it's not a decision only between field gateway and cloud, but between multiple models in the field gateway or the cloud. So we can have multiple different complexity BACS models in the field gateway and multiple different complexity models in the cloud. And the decision would be which one of those to choose in order to have as fast as possible and as confident as possible the best anomaly detection. So in the next slide, we can link all this to the previous presentation on the architecture, where we said that all the communication between the different components are being done using the Kafka service. So here we have the MEDICI, and it gets requests from the edge BACS models if the confidence is low. So if the anomaly the BACS anomaly detection said that I'm not really sure whether this is an anomaly or not because my confidence level is low, then MEDICI will have a request, and we will then decide on whether to offload this to a model in the field gateway or to a model in the cloud. And here we just see the different topics of the Kafka service. So if we move on to the next slide, this is the actual MEDICI service, where we have the request server getting the requests from the edge devices. And then we also have some servers as far as the response from the devices that the decision was offloaded to, so that we can have some execution time and confidence information to be used in our decisions, in the future decisions that we make. And we also have some network servers that are keeping constantly information about the condition of the network by probing the network. So MEDICI, what it does is it constantly collects historical data based on previous BACS execution times and confidence levels and networking statistics. And it uses all that to dynamically decide whether to offload or trigger a field gateway or a cloud model, and which one of those. So if we move on to the next slide. So the actual decision mechanism currently, at the stage that we are currently in the C4IoT project, uses two decision criteria: the total response time, and by that we mean how long does it take for BACS to make a decision of whether this is an anomaly or normal traffic, and network delays. So the total response time will include if I trigger a BACS at the cloud, how long will it take for my data to reach it and for it to make a decision on whether this is an anomaly or not. And then we also, as a second criteria, we have the confidence score of the BACS in the specific model that runs, in all the models that they run. And we have investigated various decision mechanisms. What I need to say here is that we're trying to make this model agnostic. So we don't really know what type of models BACS every time runs. It might be many different models in the same device, or it can be multiple field gateways or multiple clouds and multiple models in each one of them. So we wanted to make this as a model agnostic as possible. So we have been trying different lightweight machine learning mechanisms, and currently we are investigating how can we identify what weight should each decision criteria have in an automated and objective way, and we're using entropy in order to do that. And we're also using, testing the TOPSIS, the technique for order preference by similarity ideal solution, in order to have a decision of which BACS model should be chosen. And if we go to the last slide, I just wanted to thank you all for your attention. And if you have any questions, our contact details are on the slide. And also, if you have any questions now, feel free to ask. Thank you.
Okay. Thank you. We can move to the security at the edge now, please, Antonio. Thank you.
Okay, I will share the presentation and the video. So give me a moment. Okay, do you see the screen or?
Yes.
Okay, so I start the video. Okay, so I will start. So my name is Antonio. I am from Infineon. Regarding in the C4IoT framework, we Infineon are in charge of enable hardware security in IoT devices, in the smart factory use case, as well as in the logistics inbound logistics use case. So in order to introduce this presentation, I start wondering the question why hardware-based security is important. Why is it important to protect the devices in the hardware level? So in order to start talking the different technologies to protect the device in hardware level. So in this table, we can see different technologies to protect the devices against attacks. For example, with hardware security, your device are very vulnerable because as long as there is software bugs, you might lose your crypto material or execution or something a wrong way, etc. Using a trusted execution environment, it's a bit better, but by trusted execution environment, we build here building solutions that some architecture. Sorry. Okay. There are some architectures have like Intel, for example, Intel has the Intel SGX, for example. Trusted execution environment is in the same chip as the main application microcontroller, but a little bit isolated, and is still vulnerable with architectural attacks or physical attacks like side channel attacks or probing attacks. You can try to using memory leaks or timing analysis in order to perform some attacks. So this is because we need to improve the security at the hardware level using a security controller. So in C4IoT project, we have two main hardware security elements. One of these is the optical trust M, And another, I explain later, is the Optica TPM. So the Optica Trust M is oriented to use in microcontrollers. For example, in this board, you can see in the screen, it has a ARM chip with a Wi-Fi module that we can integrate the secure element in this board, which it only has to use a I2C interface. It's extremely small and is very low power consumption. It has through random number generator, which allow to generate keys with a high entropy and support all the typical operations. For example, the signing, verification, key generation, key derivation, and so on. Basically, all the functionalities to manage cryptographic keys. With this Optica Trust M, we provide a lot of resources, for example, to integrate with Arduino using an Arduino Shield, or even with an IRM microcontroller, because only you need a I2C interface, or even with a Raspberry Pi, because there's a API to use with this kind of devices in Python that you can perform some operation. And there's a lot of resources in GitHub, and it's very easy to use, and for microcontroller is perfect, fit perfect. The second device that we use in C4IoT is the Optica TPM 2.0. Differently from the Optica Trust M, this device is a standard by the Trusted Computer Group. We just make a hardware implementation of this standard. It's a bit more complex than the Trust M because this device has advanced features. For example, remote attestation, trusted booting, shielded keys with password and pins. And this is because this device fits more with devices with operating system support. For example, Raspberry Pi with Linux or laptop with Windows. Actually, the last standard of Windows 10 enforces to use a TPM in his devices. So probably your devices has a device like this. This device allows to make measurements over the hardware and operating system and detect possible attacks, for example, in the booting process. So, as a comparison with the last slide, we can see the devices that support the TPM 2.0. So this is a device for operating system devices, for example, Raspberry Pi or a laptop. You can use it to make cryptographic keys, to perform some cryptographic operations, or also for open SSL communication with a server. And finally, for an overview, we can see a comparison between two devices. Basically, the Optica Trust M is oriented to use with microcontrollers, and the Optica TPM is fit more with high power devices, high power consumption devices. And finally, in the last slide, to talk about the integration in this element in the C4IoT framework architecture. So in C4IoT project, we have edge devices interconnected between in a blockchain network. So the edge nodes are Raspberry Pi with a TPM. These TPMs are in charge to store the keys in order to interact with the blockchain. The TPM works as a hardware wallet. The subcomponents, the blockchain in one side and the TPM working together thanks that both components share the same standard in the software communication. That standard is the PKCS 11. This is a cryptographic standard to allow the management of cryptographic material stored in the hardware wallet by external application. In this case, Hyperledger Fabric. So finally, TPM is the responsible to store the keys and the certificates which are used to interact with the blockchain. This allows to register user, admins, and sign transaction to the blockchain. this is all for my side. And I stop sharing and Zoran.
Thank you. Thank you, Antonio. Next speaker should be Dragan and Zoran from BAT.
Okay, do you see my slides?
Yes.
Okay, great. Hello, everyone. My name is Dragan Danilovic. I'm coming from the VIP Mobile. VIP Mobile is a mobile operator from Serbia. And together with my colleague Zoran Gajica, we will present and go through overview of narrowband IoT technology by itself, and also some security procedures and best practice applied that could be applied from the mobile operator side regarding security. Okay, let me start. From the very beginning of the project, there was strict edge device requirements regarding power consumption, security, and possibility to send data and to send and receive data at any radio condition. So logically, we decided to use narrowband IoT technology as a primary one for logistical case. For logistic case, sorry. I say primary because our edge node is capable also to use 2G and LTM if it is needed. Narrowband is a new cellular radio technology specified by 3GPP in release 13. It is specifically designed for connecting edge device with low bandwidth requirements using low power while providing the wider and deeper network coverage. Actually, everybody knows that IoT can be used on any mobile technology, but there is some great benefits from the narrowband IoT at the first place regarding power consumption. Long battery life is a must. Some studies and experiments shows that even 15 years on one battery is possible, of course, depending on operation conditions. The second one is extended coverage. The technology provides improved coverage up to 20 dBs gain for the maximum coupling loss compared to 2G. It also brings some other benefits like low device cost, low deployment cost, and of course support of massive number of IoT devices. And what about security? As you see, because it is uses existing cellular infrastructure, narrowband IoT comes with security built in. Sorry, I see now that I didn't put in presentation mode. Security concepts are well covered in all areas of mobile network, even without additional hardware. Why? Because we are using a subscriber mobile identity card to protect traffic from edge node and our core network. Thanks to a set of protocols, certificates, and best practice applied simultaneously at the BTS, at the base station receiver, and also at core network. As it's shown on the picture below, field gateway is located in a mobile operator premises, protected by strong security mobile operator infrastructure. The reason for moving field gateway into the mobile operator premises is a trusted environment for safe and secure communication between edge node and field gateways. The edge node is directly accessible only from the field gateway in such a way that no data exchange between the field gateway and edge node will ever leave trusted mobile network infrastructure. So what does it mean? The best way to protect your IoT device from the internet attacks is preventing IoT device to communicate over the internet. So actually we did that in our project. Instead of additional protecting, let's say, of 1,000 devices all over the world, we protect only one. We protect our field gateway, and field gateway is the stronger hardware device, and a set of firewall rules and VPNs could give us additional protect when device sending data during offloading procedure to the cloud. Security in the mobile network relies on the standardized technology, security policies, and encryption algorithms provides the confidentiality of user data and prevent hackers from attacking our edge node. Plus, being a global standard, the mobile technology like narrowband IoT benefits from the large ecosystems of the vendors and experts, which constantly review and enhance security, functions, and algorithms as a new threat arise. That was from my side. Now I would let speak my colleague Zoran about algorithms.
I'll leave you in charge of the presentation. Okay, so can you just
no problem.
Slide. Thank you. Okay, my name is Zoran Gajca from VIP Mobile. Dragan already explained the role of the VIP Mobile operator in scope of this project. Okay, the purpose of this part of the presentation is to show the security on the air interface. You moved to the next slide, Dragan, sorry.
Sorry.
Okay, thank you. So in the logistic case, we will use VIP Mobile's full capacity to provide the communication, and the specific part of this communication is over-the-air communication, since the logistic case will be trucks and let's say our user equipment will be moving. So first of all, I just want to show the architecture of our LTE network, which supports NB-IoT implementation. So practically, we have something that is called EPS, that is Evolved Packet System, and it consists of two parts of radio network, that is access network, and the core network, so left and right respectively. One name for the radio network, so the most known name is LTE, long-term evolution, and the core network is known as SAE, that's Service Architecture Evolution. So basically, we have two types of communication. We have user data communication, that is known as user plane, and control plane, or the signaling data. So we have to protect both of them. And it is protected on the access stratum and on the non-access stratum. So when we say access stratum, we mean between the user equipment and the eNode B, that is the base station, and non-access stratum, that is direct communication between user equipment and the core network. So what will guarantee our security? This is, as I already said, this is communication secured by design. So first of all, dedicated license spectrum. It is regulated for each state and each operator, and it provides that interference is minimized from any other radio access technologies. And the security procedures are implemented in two ways. One is authentication for access the network, and the other is encryption, which will provide confidentiality and integrity of our data, both user data, the payload, and the signaling data. So when we are talking about authentication, this is a process known as AKA, authentication and key exchange access. And it is in some way inherited from the previous radio access network technologies, but also enhanced. So what we have in each of our devices is a SIM card, USIM card that everyone knows what it is. And here we have a stored secret key, and authentication is performed that in a way that each side proves that it knows this secret key. So user equipment and the network. And the network part that does it is HSS, that's home subscriber server. And this is the communication in control signaling. So from user equipment to, as you see it on the picture, through MME, that is mobility management entity, to this HSS server, which has a functionality that is called authentication center. So each part have to prove that it knows the key, and what is good about it is that this key will not be on the air. This key is not exchanged during this authentication procedure. But some calculations will be done, and each side will have to compare the results. So after comparing, there is the result is called authentication vector, and it consists of couple of intermediate results, let's say, some temporary results, and the user equipment sends its result to the HSS and vice versa. So when compared, if they check out, then we can say that the authentication procedure is done. And that is what is called mutual authentication of user equipment and the network. So that is the authentication process. And when it finishes, the user equipment and the core network agree about the algorithms they are going to use and the cryptographic keys they are going to use. And there are three types of keys: keys for user data traffic, keys for access stratum signaling. As we said, that's radio signaling between user network and eNote B, the base station, and non-access stratum signaling, which is signaling between user equipment and the core network, and that's MME on this picture. The next step, encryption, that means ciphering, and integrity check is what is going to be performed, and there are a series of algorithms that are negotiated in this AKA phase, and after that, that will be performed. Ciphering or encryption will be performed to protect the data from eavesdropping, from it being received to the third party. So it's basically confidentiality and integrity protection that will allow, let's say, to detect packet insertion or replacements, to check the integrity of the messages, to authenticate the signal messages. And ciphering is, Dragan, you can switch to the next slide. It's important to say that ciphering is appended on all communications, so user data and signaling data. And we must say here that signaling data, let's say, is more important. So the integrity check is performed only on signaling data, on a signaling plane. So now there is a number of authentication algorithms for ciphering, for encryption. The algorithms that are used in LTE by standard, by 3GPP standards, are called EEA algorithms or EPS encryption algorithm. And there are two types of algorithm for this ciphering. The one is known as SNOW 3G, that is inherited from UMTS, from 3G mobile network. And the another one, the new one, is called AES, Advanced Encryption Standards, used in LTE. So they're practically very similar. They belong to the family of symmetric synchronous stream transfer, let's say. So they are stream-oriented, very simple bitwise operations, XOR-based algorithms. And the difference is that the first one is more, let's say, stream-oriented, and the second one is block-oriented. So it is important to know that this security function is never turned off. So while in scope of signaling and in negotiation of these algorithms, there is a 4-bit field that is exchanged, which define which algorithm is used. And so we have so far 3 combinations. First one is null confidentiality protection, so null ciphering. Second one is EEA1, that's the first algorithm, and third one is EEA2, that's AES, this second algorithm. So it's the first case is practically the security function is turned on, but no ciphering is applied to data. And that is only possible if there is no SIM card. Let's say you are using the device just to make an emergency call. That's why it is allowed. And that is for the encryption of data. Another thing is data integrity protection, which is applied for signaling, and it is basically the same. It's just the names are different, so it's not EEA but EIA, which means EPS integrity protection, and the same. These algorithms are being used. So null algorithm, which means no integrity protection, again in the same case when you are having the emergency call, and two other cases, one of stream-oriented ciphering streams no, and encryption-based algorithm AES, so advanced encryption algorithm. So there are some techniques or cases where you can, so as we said, we have ciphering and integrity protection for signaling and just ciphering on data, on user plane. But we can, let's say, apply this integrity protection also for the data if we send it through these signaling messaging, through control plane. And that is called DONAS, data over non-access stratum. And it is used in the mobile practice, like one example is SMS, and of course NB-IoT supported. So these are the security procedures for air interface in the VIP Mobile or any other operator that uses LTE. And that's all from my side. Thank you. I think Milan is now taking the mic.
Thank you.
Hello, hello everyone. Can you hear me? If you can hear me and see me, we should be ready to go.
Yeah, we can hear you, we can see you, yeah.
Okay, great. So I will tell you a few words about the edge node design for the logistics use case. This is in a sense the evolution of our edge node that we previously designed, which was more of a general purpose edge node. And now we are in the middle of the fabrication of the second generation of the edge node, which is specifically tailored to the requirements for the logistics use case within the scope of C4IIoT project. So first, I will give you a brief overview regarding the requirements. The guys from VIP Mobile gave a nice overview of the NB-IoT as the enabling technology, but there are still some shortcomings of the NB-IoT. The first one is that narrowband is narrow, so we can send and transmit a limited amount of data, and in cases when we need to send more data, it's kind of limiting point. So we need to use some communication technology with higher data rates. For example, if we want to update the firmware image over the air, we should use something with higher data rate, and LTE-M is machine-to-machine technology which belongs to the scope of LTE, as well as the NB-IoT, and provides the higher data rate. However, as these nodes will be used on containers carrying car parts from the manufacturing plant to the assembly plant, we need to provide connectivity all along the route. So in cases when LTE carrier might not be available, we still need to have a fallback, and for that reason we want to be able to use EGPRS, which belongs to the second generation of mobile networking, but it's still widely used and widely available. Second, when it comes to the onboard sensing, when we were talking with people from FIAT, they told us that they have needs to locate the containers. So we need geolocalization data provided by GPS or GNSS. Also, they need to monitor vibration and vibration data. So we use the inertial unit, which is detecting vibration and magnetic field along 3 axes. So it's a 6-axis inertial measurement unit. And third thing is we need to sense the environmental parameters, which is air temperature, humidity, pressure, and luminosity. And of course, we need also to provide means to attach other kinds of sensor if there is a necessity. When it comes to the MCU, we are now at the low end of the our edge ecosystem. So we are using the MCU, which is featuring low power operation that is in the level of magnitude of microamps or nanoamps. And also we need to have the capability to run the lightweight anomaly detection, which has been described by Sergem previously. And finally, we need to have security features, which is temporary resistant storage for encryptions, keys, and certificates and other credentials. Also, we need a crypto coprocessor to offload the computationally heavy cryptographic algorithms from our resource-constrained MCU. And finally, we need to have a good quality random number generation. So now I present our edge node architecture. When it comes to the communication, we use the QuickTel BG96 module, which is kind of all-in-one. It features NB-IoT, LTE-M, also has GPRS fallback, and it also has integrated GNSS module, which we will use for the localization. As you can see, there are both multi-band GSM antenna and GNSS antenna on board. The second thing is the microcontroller, which is, as I previously mentioned, resource constrained. It's ARM Cortex M0 Plus unit running at 16 megahertz. We have 256 kilobytes of flash program memory and 32 kilobytes of static RAM. But we used the same MCU with the previous version of our edge node, and it turned out that it is capable to run the lightweight autoencoder. Okay, about the sensing part, I already mentioned what kind of sensors we have. There is a 6-axis inertial measurement unit, plus the environmental sensors and the ambient light. And we also have here a microbus connector, which allows us to attach additional click boards containing sensors or actuators or whatever we need. And finally, when it comes to the data security, we have integrated the crypto chip, which is Optiga Trust M, as described by Antonio. So I won't get into details. I will just mention once again that it is capable to run asymmetric cryptography, both elliptic curve and RSA, and which is compatible with state-of-the-art security algorithms, namely TLS 1.2, but also TLS 1.3 as the last version. This is pretty much it for me. Thank you for your attention, and the floor is yours.
Thank you. Georgos, could you say a word? Thank you. The future steps.
Yes. So yeah, thanks all the partners that presented. Very interesting presentations. Let's close this webinar by showing the time plan of our project and what lies ahead. As mentioned in the beginning, we are now at month 16, and we have completed the project setup phase, including project requirements and the preliminary business models. Also, we have completed at month 12 the minimum viable project that was presented before. So our future steps now include the release of the first degraded version. This will happen by the end of this November. By next May, we will also have defined exploitation and standardization landmark. The final version of C4IoT will be released by November 2021 and will include the whole architecture as well as the execution of our demonstrators. And finally, by May 2022, we will have the complete release, including any final assessment, impact analysis, as well as the business plans. So you can visit our website for more details, as well as follow us on our social media to keep up to date for anything that happens to the C4IoT project. We are available at Twitter, LinkedIn, Facebook. You can see the links at the bottom right of this slide. And with that, I want to conclude our first webinar / InfoDay and open the floor to the audience for any questions or feedback that might have. Thanks. So if we don't have any question, I think Marie-Noël, we can conclude
Yes.
this webinar.
Yes, just thank you all for, thank you the speakers and the attendees of this first webinar, and feel free to send your question, if any, on this site, on this website. Thank you. I close the webinar. If no more questions. Bye-bye. Thank you.
Okay, bye everybody.
Bye.
Have a nice day.
Bye.
Thank you.
Thank you. Bye.
Thank you.
Bye.